Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, dear students. Welcome back to this TV Learning Series program. As usual, I'm Teacher Patrick, and I will be with you in Senior 6. So, Senior 6 students, you are expected to be there with me. Please, I beg you to pay attention as we go through together. Either we revise or we are starting the new lesson together. In the previous lesson, if you remember very well, we had talked about some of the, we talked about the benzene, the structure of the benzene, if you remember very well, looking at the timeline of the benzene structure. That was the Kekure's model structure. And we talked about the chemical properties of the benzene and, even the physical properties, if you remember very well. And if you remember, again, the type of the reaction, that is the most important part that each of you should not forget. The electrophilic substitution reactions. Today, together, we'll be looking at we are now in the next, it is slightly almost the same part of the unit, but it is just a difference. So we are just looking at the derivatives of the benzene. So we've been looking at the benzene. This time around, we're just going to look at the derivatives of the benzene. And then we look at the effect of the substituents on benzene ring. So that is when you have the benzene. So take an example. This is a benzene structure. If this is the benzene structure with the delocalized electrons. And then we are talking about if there is a substituent. So this is what we are talking about. This is the substituent. So the substituent is that group that is attached on the benzene ring. So we are going to look at the substituents. And in the substituents, they are just divided into two parts. We have the deactivating groups, and then we have the activating groups. Please pay attention so that you don't miss this. So before we look at the groups, I wanted us to first briefly go through some simple exercise of the reactions that we looked at in the previous lesson. This is the simple exercise. Write a balanced equation to show combustion of benzene. I hope everybody can do this. Can you write it down just within a few seconds? Just maybe more or less, not more than 5 seconds. Just write down the balanced equation to show the combustion of the benzene. Right. Check whether your equation is similar to this. So let's look at we'll write our corrections here so that we can check together whether we have the same answers. Benzene. So you can use the molecular structure, say 6H6 plus oxygen. Remember, when we are talking about the combustion, we are referring to the reaction with oxygen. That is the combustion, or commonly referred to as the reaction in air. So that is oxygen. This will give carbon dioxide plus water. We said a balanced equation. So the number of carbon atoms, the number of atoms must be balancing. So we have 6 over there. This is 6. And then the hydrogens, these are 6. Here we have, these are 2. So make them 6 as well. So we are remaining with the oxygen atoms. How many? We have 2 this side. We have 12 and 15. So this is the same as 15 over 2. So that is the balanced equation. This one exists as a liquid. This is a gas. This is a gas. This is a liquid. So benzene, because of high carbon content, when it burns, it produces the carbon dioxide and water, but with some components, with some particles of the carbon that will be produced. So it burns with a soot frame. Soot frame. Or we can call it a smoke frame. So that is part A, number 1. So let's look at copy and complete the reactions below. Chlorine is reacting with the benzene. Do you remember those reactions that we looked at? Yes, I think so. So we have benzene. That is, benzene is reacting with chlorine. Does it react at room temperature? Do you remember the reactions that how chlorine reacts with another reaction? We have the similar reaction here, but here we have another reaction with aluminum chloride, which is a Lewis acid. Do you remember some other conditions under which benzene reacts with chlorine? I hope so. Presence of sunlight. So this reacts with chlorine in presence of sunlight, and this undergoes radical substitution reactions. So chlorine will be substituted. So this reaction involves the breaking or the destruction of the delocalized system of the benzene ring. It is free radical substitution. If you remember, such reaction we looked at in alkanes, free radical substitution. Then we have another reaction here with hydrogen. So similarly, benzene, that is part 2, benzene will react with the hydrogen to produce cycloalkane. This is cycloalkane. This is cycloalkane. It doesn't have. So this reaction also involves the destruction of the delocalized system of the benzene ring. This is cyclohexane. Cyclohexane. This is an alcohol. So the conditions, we have another reaction here. Chlorine with the aluminum chloride. So this is a substitution reaction. Substitution. So the benzene is substituted. The structure of the benzene. So if we can have, I hope you have taken this reaction down. So we have the benzene reacting with chlorine in presence of aluminum chloride or any other, not necessarily aluminum chloride, any other Lewis acid can be used. So they can be iron 3 chloride, aluminum bromide, or any other Lewis acid that you can think about can also affect this. So this one will produce substituted chlorine with hydrogen chloride. State the conditions for reaction in 1 and 2. The reaction 1, we have already stated the condition. So the condition is sunlight. So that reaction takes place in presence of sunlight. For this one, hydrogenation, the conditions are here. In the conditions you have, we call it Raney nickel at 150 degrees Celsius. This Raney nickel is fine grains of nickel aluminum alloy. Fine grains of aluminum, so it is very smooth, increasing the surface area under which the reaction takes place. So right away, I hope you have taken down some of these reactions below. So right away, we are going to the effects of the benzene ring. And we said there are 2 parts, so we'll have to combine them all together. So looking at these effects of the substituents but there are actually mainly 2 groups. We have the saturated groups. These are called ring activators. Ring activators. 2 and 4, what does that mean? That the 2 and 4 directs the substituent. So if you have a substituent, you have an alkyl group on the benzene ring. So that alkyl group will direct another substituent to position 2 and 4. That's what it means by writing 2 and 4 in here. So you have unsaturated groups. These are called ring deactivators. Ring deactivators. So these ring deactivators direct other substituents. That is, if you have a nitro group, it will direct on the benzene ring. It will direct other substituents to position 3 and 5. These are called, this is ortho and para positions. Ortho and para positions. That is 2 and 4. And 3 and 5 are called meta positions. So we have exceptions on the ring. When you have halogens, halogens are exceptions. For them, they deactivate the ring. I'll just talk about what we mean by activating and deactivating. So they deactivate the ring. You remember when we said ring activators direct other substituents to 2 and 4 positions. Remember that. So, but when we go to the halogens are exceptions. They deactivate the ring, but still direct the incoming substituents to position 2 and 4. So you should take that one, so you shouldn't forget. So what do we mean by deactivating? What do we mean by activating? So when we're talking about, for example, so other substituents, so we have said effects of substituents. So these are the effects, number 1. With the effects, with number 1 will be activating the ring, or make the ring, or makes the ring more reactive than benzene, than the benzene itself. 2, this activating the ring, that 2 is deactivating the ring. That means make the ring less reactive. So again, another important that we need to note down is that the activating groups direct other substituents. That is, activating groups direct other substituents to position 4 or position 2 and 4, where we have said that is ortho and para positions. Deactivating groups directs other substituents to position 3 and 5. We said these are meta positions. The meta positions are 3 and 5. So we may also mention exception for halogens. For halogens, remember what we have said, that halogens are ring deactivators. but they direct other substituents to 2 and 4, which is similar to this. Deactivators, so they have the same effect as the ring activators. So they deactivate the ring, make it less reactive. So what do we mean when we say that the ring is made more reactive or the ring is activated? This is what we are saying. For example, I will take an example of an amine group. An amine group attached on the benzene ring. This is the benzene ring with the different, so this is like this, like this. So let me use some different colors so that we can be able to see what is happening. So what do we mean by activating the ring? So this amine has got the lone pairs, remember? So these lone pairs on the nitrogen atom are able to interact with the benzene ring. So they enter into the ring. And when they enter into the ring, what happens? This is what happens. So these electrons are entering here. So when they enter, a double bond will be formed. You see, this carbon will not be obeying. If the double bond is formed here, the carbon will not be obeying the octet rule. The number of electrons here on the carbon will be more than 8. So that forces the electrons, this bond, to break out. This bond breaks out and then forms this compound. These are resonance structures. So I'll just have to, this is what happens. I remember we had this one here, and we had this one here. Oh, this blackboard is a bit. So we have the double bond has been formed here. And remember, we'll have a lone pair of electrons because this bond now breaks out. You see where the position, where the electrons are located? So that means this position has high density of the electrons. Now this carbon is satisfying the octet. So these electrons would want to again enter into the ring. So when they are entering into the ring, these electrons here, when the double bond also forms here, so we'll have this one breaking out. So the electrons will be now moving to this carbon atom. So when they move to that carbon atom, this is the structure now that is formed. So you have, this is the structure which has been formed. So you have the lone pairs now occupying this position with a bond. Now this bond now comes here. This is a bond that has been formed here. You remember we still have this one here. So this is double bond still with NH2. Something very important that I shouldn't forget is that this, after donating the double bond, after losing these electrons, when they enter into the benzene ring, this nitrogen becomes positive. So this positive remains there. So these electrons would also want to enter into the ring. So what happens then? These electrons come in the ring. So when they enter into the ring, this is what happens. So these electrons are entering here. So this one have to break away again. So this one has to break away and form lay electrons on this carbon atom. So this will come to this compound. So you have a bond here, which has been formed. You have another bond here. So you have some electrons which are being formed here. And then you'll have your electrons here with the positive charge over there. This is a positive charge. Remember, that is the positive charge that was formed as a result of the electrons entering into the ring. So what happens here, these electrons would also want, so it is a continuous process. These electrons would want to enter again within the ring. So when these electrons are entering into the ring, like this, so that means if a double bond is formed here, what happens? This carbon will not be obeying the octet rule, as you can see. Because a double bond formed here, the number of electrons surrounding this carbon will be many. So this bond will be forced to break to neutralize the positive charge. So eventually, this is what you come up with. The structure will be like this finally. So you are coming back to the original structure with, so this is where it is. This is where it is. Probably I can use so this one shifted to here, and this one shifted to here. And then you'll have another one was red. So this one, where did it shift? Shifted to here. See the structure here. So this one is regenerated, NH2. This is coming from this one. When you look at this structure is alternating. Look at the double bonds. Originally, this one was here, but it has shifted to this position. You see that? This bond here, which was here, now has shifted to this position, as well as this one, which was here, now shifts to this. This is the original position, so it has shifted to this. So these are called resonance structures. These are called resonance structures. So I just want to mention again, what do we mean by the activating the ring? So these are this is a ring activator. I've just taken an amine from this. Ring activator. Look at these positions. This is position number 2. Look at where the positions where those electrons were concentrated during the resonance structure. You see, this is where it is located. Look at this. Double bond. Which position is this? This is position number 4. Look at this. This position here and this position are the similar. This one and this one are the same positions. Position number 2. So meaning the ring activators, what we mean by the ring activators is increasing the electron density within the ring. So that electrophiles are positive. They are positively charged. So these electrophiles will be able to attack those positions. Why? Because those positions contain high density of electrons. Position number 2 and position number 4. So when you draw the resonance structure, you can be able to tell how the ring is being activated. Let's look at the ring deactivators. I'll just take an example of the nitro group. The nitro group with oxygen, which is a single. This is nitrogen, and this is the benzene. This is the benzene ring with the positions. Maybe I can take this one. This is the double bond there. When there is a double bond, there is another one here, and there is another one. So that is the nitro group. So on the nitro group, this nitrogen contains a positive charge. That's the formal charge. So what happens really, that positive charge is naturally, because this nitro group itself has a natural resonance structure. These are lone pairs over here. So these lone pairs can also enter here as this one also pulls out. So, but that's not what we are looking at. What we are looking at is what happens within the ring. So what happens here, these electrons would want to get out of the ring. Why should they get out of the ring? Because they are looking for this positive charge. So that positive charge, that means this one will become positive. This here will be, that position will become positive because the electrons have moved away. So meaning that this bond will have to break away, and then that is, it shifts the position to this part. So we'll have the nitro group in that position. So this one has, so this will have this one, we're shifting to this position. And then you'll have the nitro, oh sorry, I have to use different colors so that this forms a this is positive. We said this is oxygen with a negative charge. So this was positive here, so the bond, this bond has shifted to this position. So when it shifts to this position, this one becomes positive. Do you see what happens here? This one becomes positive, and therefore, what will happen? This one will have to move to neutralize the positive. So this bond has to shift again. So this one will come to this. So you'll have this one. You'll have this position. Now this one has. So this one will become positive. So when it becomes positive, this is where it comes from. So this one has shifted to here. So you'll have a double bond over here. This is oxygen, and this is oxygen with a negative charge. So here, still, because we have said this one forms, so what does that mean? It means now this double bond will have to come again. So this double bond will want to enter into the ring to form, to neutralize that compound. So this becomes 2. So we have the position here and this one. So the double bond has broken away. And as it breaks away when it is coming, this one comes back again. And then you'll have the oxygen with that oxygen over there. So we have, these are also, when you look at this, the electrons were moving up. They were being pulled out of the ring. They're moving out of the ring. And what happens? Look at where the positive charges have been formed. This is a positive charge. We had a positive charge here. And then we have another this is a positive charge. This is position number 2. And this is also position number 2. This is position number 4. What does that mean? That those ones cannot be attacked by the electrophiles. So electrophiles only have to attack other positions. This is position number 3 and position number 4. This is position number 3, number 3 and number 5. Those are meta positions. So that is the resonance structure of the nitro group, which is deactivating, removing the electrons within the ring. So I beg to stop here, but first of all, I will just want to give you an exercise that you'll have to cut out. Use the archive group. Use the archive group to show the resonance structure of the methyl benzene. That is number 1. That is A, B. Use an aldehyde to show how it deactivates the benzene ring. Thank you so much for watching and listening. I hope to see you in the next lesson. Have goodbye.